all. In this lecture session, we are going to cover single phase AC voltage control with resistive inductive load. So the difference between previous circuit and this circuit is it is lies in your load. So in previous case it is only resistive load, now it is resistive inductive load in the output. The source side and the AC voltage control side there is no change. However, as it is RL load, definitely there will be a phase angle between voltage and current. So if you consider that as phi, so based upon this phi and firing angle alpha, we are having different operating modes of this single phase AC voltage controller with RL. So let us consider alpha firing angle is greater than the phase angle, then we are going to have discontinuous current. So we are going to have discontinuous conduction mode. So if firing angle is equal to phase angle, then it will be continuous current or continuous conduction. So if firing angle is less than phase angle, it is also results in continuous current or continuous conduction mode. So based upon the relation between firing angle and the phase angle between voltage and current, we are having three possible operations for this single phase AC voltage controller with RL load. So we'll see first thing, when firing angle is greater than phase angle. So consider a source voltage. So based upon the zero crossings, triggerings and extinction angles, we can decide the modes of operation for one complete cycle. For that, first indicate the zero crossings. Pi, 2 pi, 3 pi are the zero crossings of the source voltage. So these are indicated with dark block lines in this figure. So after indicating the zero crossing instants, indicate the triggering instants alpha, pi plus alpha and 2 pi plus alpha. Alright, so these three are the triggering instants. So next indicate the extinction instance. So as far as this 0 point is considered, first beta instant will be this one beta and next beta instant will be pi plus beta, and this first red line belongs to the previous half cycle beta instant. So beta instant is nothing but that the load current becomes 0 at this point. So discontinuity, if beta is there, your load current is discontinuous. So we have identified the beta instants also. So what are the things we have identified? Zero crossings, pi, 2 pi, 3 pi, triggering instants alpha, pi plus alpha, 2 pi plus alpha, extinction instants beta, pi plus beta. These are for these with respect to 0 point, and this beta instant from the previous negative half cycle. That's why I have not given any name to this red line, that is for extinction angle instant. So mode 1 can be started from alpha for simple understand. So alpha to beta, triggering instant to extinction instant, and mode 2 can be from extinction instant to next triggering instant beta to pi plus alpha. Mode 3 triggering instant to extinction instant. Mode 4 extinction instant to next triggering instant 2 pi plus alpha. So we have started at alpha, ended at 2 pi plus alpha, so the duration is 2 pi. So we can analyze for one complete cycle by using these mode boundaries. Alright. So my first mode is from alpha to beta, second mode is from beta to pi plus alpha, third mode is from pi plus alpha to pi plus beta, fourth mode is from pi plus beta to 2 pi plus alpha. These are four modes. So we'll start with first mode. At alpha, triggering pulse will be given to T1, it goes to on state. T2, it will be in reverse blocking, that is off state. Then Vt is equal to Vs, sorry, V0 is equal to Vs, I0 starts from phase, T1, resistance, inductance and neutral. This is the current path for the output current. Then Vt1, thyristor 1 voltage will be on state voltage drop. Similarly, thyristor 2 voltage also will be on state voltage drop. This will be positive and this will be negative. So mode 1 is completed. Now mode 2. At beta, the current flowing through the T1 becomes 0. Already reverse voltage applied to the T1 at pi, so T1 goes to off state, that is reverse blocking at beta, and T2 will be in forward blocking mode, so that output voltage will be 0, output current will be 0, Vt1 will be Vs, Vt2 is also Vs, but it will be negative, it will be positive. Now in mode 3, at pi plus alpha, triggering pulse is given to T2, so that it goes to on state. T1, it will be in reverse blocking off state. So V0 is equal to Vs, but the current path is from neutral to inductance to resistance to T2 to phase. This is the current path for output current. Then Vt1 depends upon Vt2. So Vt2 will be on state voltage drop, so that Vt1 is also on state voltage drop. This will be positive and this will be negative. Similarly, mode 4, at pi plus beta, the current flowing through the T2 becomes 0. Already at 2 pi, reverse voltage is applied to T2, so T2 goes to reverse blocking, so that off state. So T1 will be in forward blocking, still off state. Alright, so V0 is equal to 0, I0 is equal to 0, Vt1 is equal to Vs, Vt2 is also Vs. So this will be positive and this will be negative, as it is reverse biased. So we are having information of all the four modes, so we can easily fill the waveforms. First, we'll start with current, as it is RL load. So at alpha, the current starts from 0, it increases to some maximum and it becomes 0 at beta. So when T1 is in conduction, so I'm assuming that the current is flowing from phase to neutral, so that I'll draw the positive half cycle from alpha to beta. So beta to pi plus alpha, the current is 0. Now pi plus alpha to pi plus beta, the current flows from neutral to phase, so I will draw the negative current, and this current becomes 0 at pi plus beta. Now again 2 pi to 2 pi plus alpha, the current is 0 and it goes to right. So this is the current waveform. Now 2 pi to 2 pi, this red line I am having some negative part, so that I'll write some negative part and then 0 here. Current waveform is completed. Now when it comes to output voltage waveform, in mode 1 the output voltage is Vs. So it continues up to beta. So pi to beta, I'm going to have negative part. So in mode 2, voltage will be 0. In mode 3, so it follows the source voltage up to pi plus beta. So pi plus beta to 2 pi plus alpha 0. Then again positive half cycle. Now if I redraw here, this will be 0 and this will be positive part. Now in mode 1 alpha, so thyristor on state voltage drop and from here to alpha to beta. In mode 2 beta to pi plus alpha Vs negative. Then pi plus alpha to pi plus beta Vt negative. Up to here. Next pi plus beta to 2 pi plus alpha positive Vs. Then it will be plus Vt. So here also we are going to have plus Vs. Here it will be minus Vt. Now similarly for thyristor to alpha to beta, it will be minus Vt. Beta to pi plus alpha, it should be plus Vs. Pi plus alpha to pi plus beta Vt positive. Pi plus beta to 2 pi plus alpha Vs negative. And then negative Vt. So before that it is negative Vs. And this is positive Vt. So these are the various waveforms for output voltage, output current, thyristor voltages for discontinuous current. So if you observe here, phi is equal to beta. So this beta instant is less than alpha instant, so that I am going to have discontinuous conduction mode. That means discontinuous means output current is having zero value for some duration. Alright, so next we can go through the textbook waveforms for better wave shapes. From this we can calculate V naught RMS. So generalized formula for V naught RMS is integral 1 by T. So T1 to T2 Vs square d square d omega t. So this entire term is under root. Total time period is 2 pi. So actually I need to integrate from alpha to beta, then pi plus alpha to pi plus beta. Anyway, it is not necessary as it is following half wave symmetry. So alpha to beta Vs square means Vm square sine square omega t d omega t. So as it is following half wave symmetry, I can multiply with 2. So root. So 1 by pi integral alpha to beta. Here I can write Vm square. So sine square omega t I can write 1 minus cos 2 omega t by 2 d omega t. So if you solve this, Vm by root 2 pi beta minus alpha plus 1 by 2 sine 2 alpha minus sine 2 beta. This entire term is under root. So this is your V naught RMS value with RL load with discontinuous conduction mode. So once again, if we go back to this, simply we have identified the zero crossings, triggering instance and extinction instance, and we have divided this one complete cycle into 4 modes, and based upon the switching conditions in these modes we have identified the output voltages, output currents, thyristor voltages. So we have finally drawn the waveforms from this information, and finally this is your RMS output voltage. So this is about discontinuous current. Now when alpha is equal to 5 and alpha less than 5, both the cases the output waveforms are same. So let us consider this as 0. So 0 to 5, here from the previous half cycle T2 will be in conduction. Now 5 to pi plus 5, T1 will be in conduction. So pi plus 5 is nothing but pi plus alpha. Now pi plus 5 to 2 pi plus 5, nothing but again T2 will be in conduction. So here phi is equal to alpha. So pi plus alpha to 2 pi plus alpha, alpha to pi plus alpha. So we are going to have continuous conduction. So both output voltage and source voltage are having same voltage waveform. There is no separate waveform for output voltage. So both source voltage and output voltage are equal. So you can find the both output current and source current are equal, but they are having a phase difference with voltage, that is phi. So this is about continuous current mode. When my firing angle is less than phi, so let us assume here I have applied triggering pulse for T1, but T2 is in conduction here. So when T2 is in conduction, what about thyristor 1 voltage? It is negative VT. You can observe from the previous cases. So when it is negative VT, it is reverse biased. By as the T2 is in conduction, T1 is reverse biased by on state voltage drop. So you cannot give triggering pulse at this instant. So only you can give triggering pulse at this instant, so that again 0 to 5 T2 will be in conduction, 5 to pi plus 5 T1 will be in conduction, pi plus 5 to 2 pi plus 5 T2 will be in conduction. You cannot give triggering pulse in between these things because the respective switch is reverse biased by on state voltage drops during this period. So in both the cases, when alpha is equal to 5 and alpha less than 5, we are not going to get any voltage controller. In both the cases, V0 is equal to Vs. So there is no control over the output voltage in these two cases. Only the output current is having some phase shift with respect to source voltage. So these are the things we can observe in the continuous conduction mode in the both cases, alpha is equal to 5 and alpha less than 5. Thank you.